Okay, so I think we can start. This morning we have a panel on black hole evaporation. There are going to be three talks, one by Ahmed Almheiri first, Abhay Ashtekar second, and Carlo Rovelli third. Speakers will try to limit them to 15 minutes each. I suggest if there are questions during the talks, we keep them short to clarification type questions. If discussion ensues, we just move them towards the end. So Ahmed, please go ahead.
Hey, thanks. Thanks a lot for the invitation to participate in this panel. I've been tasked to talk about some results from 2 years ago on reproducing the page curve from the gravity path integral. And so let me talk about that. So I've titled the talk as Entropy of Hawking Radiation, and the question is about how to compute this entropy. To begin, let me first talk about something that some of us have been calling the central dogma of black holes. This is the idea that you should think of a black hole as a normal quantum system whose number of degrees of freedom scales as the area of the horizon divided by 4g Newton, and which evolves unitarily under time evolution. Here I mean that in the sense that a black hole is coupled to its environment, and then the total system, the combined system, is evolving under time evolution. That's what I mean. The question is whether this assumption is justified. And so this talk is going to be about evidence for this assumption or dogma. Let me first begin about what we know about black holes. So we know that black holes have thermal entropy, and this thermal entropy is assigned by the gravity path integral. The way you see this is, the way you define entropy is you first write down a canonical partition function, which is defined as a trace of e to the minus beta h. So it's a trace of some Euclidean or of some evolution in Euclidean time. That's the beta here. And what we learn from quantum mechanics and quantum field theory is that a trace of this type can be written as a path integral. Here, the theory that we have is gravity. So it's the path integral of gravity. So here it's some, this is the integration measure on the metrics. You have some action of gravity, which could be, let's say, the Einstein-Hilbert action. And there's also a partition function of the matter living on the space-time, which I'm going to leave implicit as just z of m. This integral is a hard integral to do, but one way of doing it is by restricting to saddle points. A famous saddle point of this path integral is the so-called Euclidean cigar geometry. I should have emphasized that this path integral is to be evaluated given the following boundary conditions. At infinity, in particular, you have an S1. Okay, that's supposed to correspond to the Euclidean time direction. Now, this is again the saddle point. The relevant saddle point for this integral is this Euclidean cigar, which famously everyone knows that the metric on this is just the analytic continuation of the Schwarzschild solution. Something amazing about this saddle point is that if you plug the solution back into the action and then differentiate with respect to the temperature or apply this differential operator on log of z of beta, that's just a formula of extracting the thermal entropy. What you find is that it's the area of the horizon of the black hole, which is the area at the tip of the cigar, plus the entropy of the matter outside. I'm going to ignore this second term. The upshot is that we have the upshot is that you get a finite entropy from this configuration, which corresponds to a black hole. So the upshot here is that the gravity path integral assigns a black hole a thermal entropy, and hence it seems to suggest that a black hole has area over 4g Newton number of degrees of freedom. But now, if we assume that if we take the black hole to be a quantum system, then this result suggests that we should assign the black hole a Hilbert space of this dimension. area over 4g Newton. Now, it's a theorem in quantum mechanics that the von Neumann entropy of a quantum system is capped out by the thermal entropy of that system. In this case, this means that the maximum von Neumann entropy that a quantum black hole can have is the area of the horizon divided by 4g Newton. Just some intuition behind this theorem. It's just that the von Neumann entropy of a density matrix measures the uncertainty there is in the quantum state. And the maximum uncertainty you can have is really just the total number of possible states. So
I have a question, just
yes.
clarification. Because you're going to the Euclidean, aren't you calculating the entanglement entropy of the outside only? Aren't you calculating something that has to do with the outside?
So far, I did not compute an entanglement entropy. So far, I computed a thermal entropy. And that's the number that you get.
But when you go to the Euclidean, this restricts yourself to the outside of the black hole, which is the only place where this weak rotation makes sense.
Sure. I agree. You can interpret this as saying that this is the thermal entropy of the black hole as viewed from the outside. I'm okay with thinking about it like that.
Okay, thank you.
Okay. So the upshot so far is that the gravity path integral told us that the black hole, again, as seen from the outside, if you like, has thermal entropy of given by the area of 4g Newton. If we add this extra ingredient of saying that quantum mechanics applies, then this would say that the von Neumann entropy of the black hole has to be capped out by the area over 4g Newton. Okay, but something else we know.
Maybe can I just a remark? I mean, so far I agree with what you're saying, but maybe just a point of when you're saying, you know, we're postulating that the Hilbert space dimension is bounded by the area. Maybe a word here is that in some sense, this is kind of the project of quantum gravity, right? To prove that. And this is what's hard, right? So it's, if you postulate that, you can see, but maybe it's good to acknowledge here that, I mean, there's an entire community of people that have tried to address in what sense you could make sense of that object from, let's say, canonical quantization, non-perturbative quantization, etc. Is that fair?
Yeah. Well,
this is kind of not, this is not skipped. It's a humongous assumptions to do that. And it would be, you know, having a theory of quantum gravity means understanding how that comes to be true.
I more or less agree. However, what I would say is that the result from the gravity path integral is one data point towards that result. And that's basically what I'm taking, what I'm using so far. So the gravity path integral assigns a thermal entropy as viewed from the outside. And if you were to believe that that is actually, that really should be thought of as a thermal entropy, then, well, it's really what I have on this
Yeah, but the key word
slide
is,
so far.
the key word is belief, and it's, you know, until you have a connection between a Hilbert space and a canonical definition and this semi-classical calculation, which, you know, are living in two completely different realms at this stage. So this is maybe what I'm pointing out is a point of convergence. Like if you were focusing on in what sense these two stories have anything in common, then the two communities which are here can you know, talk to each other and face the central problem, which is really to look for a proof of this assumption or belief.
Yeah. If I can summarize, well, one, I think roughly speaking, what you're saying is that what's the microscopic origin for this thermal entropy? For example, you can think of it like that. Maybe that's what you meant by well, defining the quantum states in some sort of Lorentzian quantization of the theory. That's fair. The only from my side of the, well, in string theory community, that's been further evidence of this of this conjecture comes from, counting microstates using D-branes and so on and so forth in string theory. And maybe I'll learn some other similar kinds of computations from the loop quantum gravity perspective, maybe as I hear the other talks. But I'd be happy to discuss this point more during the discussion session. Okay, so now black holes evaporate, and they do so by emitting Hawking radiation. As Hawking taught us, that there's this pair creation process that happens across the horizon, where you have entangled pairs that get emitted, and from the outside, it appears that the black hole just shrinks and gets, transforms into just these blue Hawking quanta that I'm drawing here. The upshot of the calculation is that the entanglement entropy of the outside world, if you will, of all the radiation just grows with time. Okay? But there's an assumption in this calculation. Okay, so there's what I'm calling Hawking's assumption. There are two steps to his calculation. The first step is to declare that the state of the radiation is what you get from a matter path integral on what I'm calling the black hole saddle. Okay, so you first solve for the classical solution for what the space-time looks like, and then you evaluate the matter path integral on that, and that prepares for you some state. After you get the state of the matter, which is the state that I described on the previous slide, you have Hawking quanta outside that are entangled with Hawking quanta inside, then you compute the entropy of the radiation outside. Okay, so I'm going to call this the Hawking entropy. So it's basically just equal to the matter entropy of the radiation outside. In equations, roughly speaking, it's what I'm saying. These 2 points are what I have here at the bottom. There's some density matrix, which is the density matrix of it's a density matrix of the matter in some gravitational saddle. And then the way you compute the entropy is that you take this density matrix of the matter in the gravitational saddle and you plug it into the usual formula for entropy, trace rho log rho. And when you do this, you get, as I just said, the entropy just grows with time for all time. That's the Hawking answer. Now, the issue is that the thermal entropy of the black hole, again, as viewed from the outside, just decreases with time for all time until it goes down to 0. And hence, after these 2 lines cross, there seems to be a problem. In particular, this would predict, first, it looks like the black hole is getting this is inconsistent with with what we said about how quantum black holes should behave, in particular about the number of states. Here it says that a small black hole can be entangled more than its thermal state. Okay, so it can be entangled. The amount of entanglement can be more than what the black hole has room for. And so what this says is this makes a prediction, which I think is a very serious problem. It predicts that in this theory that you can have light objects with an arbitrary number of internal states. Okay, with arbitrary large number of internal states. Okay, because as the black hole becomes very, very small here, its entanglement can be very, very large. Okay, and after the black hole disappears completely, again, it looks like black hole formation evaporation can take a pure state, say a star, into a mixed state of the radiation. And this evolution is not unitary. Now you can ask, why is this a paradox? Well, it's a paradox because so far it seemed that a set of trusted assumptions led to unpalatable conclusions. In particular, it looks like one perspective you can take is that quantum mechanics broke down. You've evolved a pure state to a mixed state. That's one perspective you can take. Another perspective is that it suggests, again, that you have these low mass, high entropy objects. And then there's going to be the question is, where are those high degeneracy small mass objects? Why didn't we see them yet? There's old work by Steve Giddings that says that you should have seen these, you should have seen signatures of such objects, say at the LHC, for example.
Okay, maybe it's a question for. Maybe this is a question for later, but as you agreed at the beginning, your account concerns the exterior of the black hole. So how can that be a full story of what is going on when you never say anything about what happens with what falls into the singularity?
Well, the quick answer to that question is just, well, first let me ask you a quick question. Was your comment about the second point here, or just about the entire thing? About the paradox?
It's about your assumption that you agreed. I mean, I understood. You're telling a story from the outside only. All your story is about the radiation outside and the size of the black hole becoming smaller as seen from the outside. What about everything? I mean, your Hawking pairs that fall into the singularity. Without saying anything about those, how can I know I'm not missing something really big?
Yeah, that's fair, but I don't think that changes anything I'm saying in this slide. In particular, this says that I'm not making a statement about what physics looks like for a person on the outside. It either looks like quantum mechanics broke down, okay, or it looks like there are these high degeneracy small mass objects. So what I'm saying is that independent of what happens on the inside, if we're saying that Hawking's answer is unchanged from the perspective of the outside, then you have a problem.
Well, okay, I don't agree with that, because if you don't say anything about but okay, we can, yeah, I can stop, sorry.
Yeah, I think we should let him finish, because I think there's a time for discussion.
But maybe, yeah, before, I think, if I may say something, you say trusted assumption. I think it really depends on which community. For instance, one assumption which people make is the assumption that the Hilbert space is split. That is, it can be split into a tensor product. And if you are a quantum gravitist, you know that this is wrong. That is, we know that this assumption is not valid. I'm not saying that it resolves all the paradox, but what is clear is that inside all these paradox, there's already an assumption that we know is not valid, which is essentially the assumption that the Hamilton constraint, which is an elliptic constraint, is not taken into account. So that, you have to say, so, and relieving that assumption doesn't mean a breaking of quantum mechanics. It means revisiting this argument in the light of the fact that the Hilbert space is not split between the interior and the exterior. Would you agree with that? That would be a less dramatic statement, which is a more accurate reflection of the proper knowledge we have about quantum field theory in gravitational theory.
Okay, let me say two things. The first is that I don't trust the assumptions. Okay, so this is trusted sort of in the past, if you will, or said differently, it's the trusted here is that well, let me just keep it as that I don't trust the assumptions made so far. The second point is that, yes, I mean, this also a comment also touching on the previous question, that the inside is important, and I agree. And I do agree that the Hilbert space of the inside and the outside is not split, but I think it doesn't split for different reasons, not for the usual reason of just because of Hamiltonian constraint and so on and so forth. It's for a more subtle reason, which I will get to in a second. And all these are great questions, but we should leave them for later.
Yeah, folks, we're at 20 minutes now, so we should let Ahmed finish.
Okay, thank you. Okay, so far this is the what we saw so far. The problem. So the gravity path integral also predicts a black hole evaporates. It's from the path integral because it comes from the quantum fluctuations about this atom. And that leads to the volume and entropy being larger than the area over 4G Newton at some point in the evaporation. But then this conflicts with the other constraint that we found from quantum mechanics. And so then you can ask, what is the weakest link? Okay, so you can say that maybe quantum mechanics should not apply; it just breaks down, and that would imply that the thermal entropy is not a bound on the von Neumann entropy. Or you can say quantum mechanics continues to apply, but then you just have some other reason for why von Neumann entropy is not bounded by thermal entropy. I think this is too drastic. I think it's just that this calculation is wrong. Like in some sense, the resolution that I'm sort of advocating for is that this result that the von Neumann entropy is larger than the area just comes about because of some mistake in a sense. Let me first tell you the answer, and then I'll justify it. The answer is that there's a new formula for computing the entropy of the radiation, which comes from the gravity path integral. Nothing new has been pulled out of a hat. Okay, and the formula is the following. So there's a new contribution from the gravity path integral. What it says is that there are two possible formulas that you can apply to compute the entropy of the radiation. The first is what Hawking applied, just the entropy of the matter outside. That's just a standard formula. Another formula is what I'm going to call the island formula for the entropy. It says that the entropy of the radiation outside is not just the entropy of the outside modes, but it's the union of the entropy of the outside along with some region inside the black hole called the island, which I'm going to call the island. So it's the matter entropy of the radiation union island, plus the area of the boundary of the island. Okay. So far, this island is not picked. It's not just an arbitrary place in the interior of the black hole, but it's fixed by some condition. The condition is that the surface X extremizes this functional here, which is sometimes called the generalized entropy functional. Okay? So given some radiation outside that you want to compute the entropy of, you have to look for the island which extremizes this. And then what the prescription tells you, again, from the gravity path integral, is that the actual entropy of the radiation is the minimum between these two contributions, between the Hawking answer and this new island answer. Well, the Hawking answer, we saw it just grows with time, while the island answer, it turns out that the matter entropy term of the radiation union island is actually a small number. It doesn't do anything really. The radiation basically is because all of the radiation outside is purified by the radiation in the island. So this is just some small number. And the dominant piece comes from the area of X, which is actually very close to the event horizon. And since the black hole is shrinking, this gives you a number. This is just a decreasing function of time, which traces the thermal entropy of the black hole. Taking the minimum between these two tells you that the entropy would rise initially and then come back down. And so you get the page curve, and it transitions. Well, this transition is sometimes called the page time. And hence the thermal entropy bound is satisfied. The way you get to this formula is by relaxing Hawking's assumption. So what Hawking did was that he computed the density matrix of the matter, where you restrict to the quantum state on the black hole saddle. Then you take that density matrix and you plug it into trace rho log rho. We went over that. The new method says, hang on, you can't do this prematurely. Okay, so you cannot take the density matrix of the outside and just plug in a saddle. What you have to do is first write down the function for the entropy, trace rho log rho, where rho is the full density matrix, and then consider saddle points saddle point evaluation of the full function here of trace rho log rho. And when you do that, you find that there are various contributions. There's a contribution coming from the Hawking saddle, and there's a contribution coming from the island. Sorry, one saddle point gives you the Hawking answer, and there's another saddle point which gives you the island answer. For the experts, so the entropy, you can write it, you can compute it by using this replica trick where you take rho to the power of n. The question is whether you take expectation, by expectation value here, I mean, you plug in a gravity saddle, then raise to the n, or you take the gravity saddle of n copies of the system. The thing that the second term gives you is that you can have wormholes that connect the different copies. Okay, when you have multiple copies, a saddle point can connect the different copies. And so what you then find is that when you do this, that you do end up satisfying this, that the von Neumann entropy is bounded by the thermal entropy. And in a sense, we didn't need to assume quantum mechanics anymore. What we're finding is that the gravity path integral is self-consistent by itself. The answers that it gets are consistent with quantum mechanics. We don't need to impose this condition. I was going to give a very brief example, very simple and brief example for this effect of how wormholes come in to fix things. But if the organizers feel that I went too far over time, we can go to the next talk. Should I keep going?
Just try to move ahead because we're at more than 20 minutes now. 25 actually.
So do you want to skip this last part or?
Move through it as quickly as you can.
Okay. So let me give you a quick example of the how. So let's consider a abstract version of a completely evaporated black hole. So here, here should think of time going upwards, and the black hole sort of, in some sense, detaches from the space-time. Again, this is a cartoon. And inside, so this thing that branches off of the universe, we're calling that the interior. And this blue line is supposed to represent Hawking particles inside entangled with Hawking particles outside. Now let me abstract this abstraction in terms of this picture. Okay, so this picture is again a black hole detaching from our universe, and there's entanglement between the inside and the outside. Suppose you want to compute the not the entropy, but the purity, which is trace rho squared of the outside. Okay, the exterior density matrix is given by taking the state, ket bra, and then tracing out the interior. What does tracing out mean? It means that you attach the interior using a gravity path integral. Now, when you compute trace rho squared, you have to multiply two density matrices by, you have to multiply these two density matrices, and that's this cross contraction here. And now you have two factors of the gravity path integral for the inside. Now you let the gravity path integral connect in all possible ways. One possible way is the trivial way, where you just connect this point to this point. And this gives you this picture here, which gives you an answer for the purity, which is 1 over k. It tells you that the outside is mixed. However, there's another connection that you can have where the bra on one side can connect to the ket of the other. That's a so-called replica wormhole contribution, which can be rearranged to factorize to be just this, which is just trace rho all squared. And hence that's just equal to 1. So this new contribution tells you that the purity, that the outside is actually pure. And that's a good approximation when k is large. Okay, so that's pretty much all I had. So just some final comments. The origin of the gravity path integral gave us an answer consistent with the central dogma. The origin of the area term that we saw, the area of the island, is the same as what you get from Gibbons Hawking. It's like it comes from the Euclidean section of the path integral on the horizon. And just with Gibbons Hawking, there's no microscopic understanding. And the final point is that the gravity path integral is good at computing numbers like the entropy, but it's not good at writing down the exact state of the Hawking radiation. That's pretty much everything I had. Thank you.
Thank you, Ahmed. Please share your screen.
So while I'm sharing the screen, I can just ask Ahmed a quick question. So is it the case, Ahmed, that the island knows about inside, even though in some sense you were always outside, but the island knows something about the inside the black hole?
Yeah, so I would say slightly differently. I would say that the radiation, so when we computed the entropy of the radiation, it had a contribution from the island, from the inside of the black hole, okay, which was important for to get the right answer. What this means is that the radiation knows about the inside. Given that the entropy of the radiation depended on the inside, hence it knows about the inside. And I didn't have time to talk about this, but you can actually show how actions on the radiation can actually modify the state of the interior. But let me keep it at that.
Thank you.
Thank you, Ahmed. Let's go to the next speaker, Abhay Ashtekar.
So what I would like to do is to sort of provide a broad perspective from loop quantum gravity side. And I think that I hope that we can make connections with what Ahmed was just saying and have some discussion on that as well. So what I'm trying to do here is really have this general consensus which has come from many researchers, and my remarks are largely taken from this particular review article from about a year ago, slightly less than a year ago. Okay, so let me start with a preamble as to what I would like to sort of communicate. I think that there is a broad consensus within LQG about 2 points. One is that for this quantum black holes, there are 2 things that are really important. One is singularity resolution, which I think is something that is ignored in many other approaches. And the point from loop quantum cosmology, we know that there are many examples in which the singularity is resolved. And in the resulting space-time is then much larger than the classical space-time that we started out with. And then the quantum state can evolve through the Planck regime all the way to Scri plus in this larger space-time. However, I want to emphasize that within loop quantum gravity, details of how to describe Planck scale physics in the black hole context are still work in progress. There is a work in very different directions. And I've only listed some of the major contributions up here. But they all sort of point to the fact that the singularity, or they all have one thing in common, which is singularity resolution. And there are results which say that singularity is resolved with various degrees of assumptions and approximations. And the second thing is really relevant notion of horizons. The main point up here is that there are no event horizons. And as I will see in some more clearly, what forms and evaporates are dynamical horizons. And these dynamical horizons are time-like during the evaporation process. And a lot of confusion can arise because of explicit or implicit assumption that there's an absolute event horizon out of which nothing can come out. As a result of these 2 things, the black hole evaporation can be unitary without having to invoke various, to us, exotic ideas such as the long time ago quantum Xerox machine, and more recently fast scramblers, and a little bit in between the 2, firewalls, etc. And also one does not have to worry about this whole issue about quantum monochrome. As in Ahmed's talk, I will not discuss full quantum regime, but already there is some tension at the semi-classical regime, which was hinted at by Ahmed. So I would like to address that. And I will summarize the LQG viewpoint on this tension. So first, I would like to explain what was in these first 2 points up here, the LQG viewpoint up here, and then the semi-classical regime up here. So again, let me just begin with the Hawking's argument. Just like what Ahmed did, Ahmed started with Hawking's argument using the Euclidean path integral, and I'm talking here about the Lorentzian spacetime. So in the external field approximation, this was Hawking's original calculation. There are 3 assumptions. One is that one uses quantum field theory on a black hole background spacetime, and the approximations or assumptions are that spacetime is treated classically. The test quantum field is really a test quantum field, so there is no back reaction on the quantum geometry. And the matter field which collapses is classical and is distinct from the test quantum field considered. So here is a typical sort of idea. The star is collapsing, and the star is never considered as a part of a system. What one is looking at is really giving some scalar field on sky minus, evolving it, and see what happens on a Cauchy surface like that, and what happens on a partial Cauchy surface like that, and what happens on sky plus as a whole. So if you want to include back reaction, then this really is to address the second part. I want to emphasize that there is no detailed calculation even today about including a back reaction. And Hawking just drew this diagram. And this diagram really did not come from any detailed calculation. I want to emphasize that because it is often forgotten. This is the general expectation that is based on the physically motivated heuristics that led Hawking to propose that the space-time diagram should be like that. Basically, the strength of the singularity decreases, if you like, as a black hole shrinks. And then finally the black hole shrinks. So people say, well, I don't know what happens here, but in the final picture, there is really an absolute boundary. And in one of the Ahmed slides, even though he was talking most of the time in the Euclidean domain, it looked like there was also an absolute boundary up here, and the particles were coming out or falling in outside that boundary. Because a future boundary includes space-time, includes a singularity, I think the statement is that the state on sky minus does determine state on sky plus, but the converse is not true. Or the state on sigma 1 will determine state on sigma final up here. Sigma initial determines, but conversely, I cannot evolve this backward in time up here. And Hawking changed his mind about this diagram. And in fact, the new diagram they propose have no singularity. But surprisingly, the original diagram is still very heavily used in many of the arguments. And it is still assumed, therefore, that the correlations should all be restored before this last ray, which is called the UAT for the event horizon, because this is the future boundary of the past of null infinity. And the statement is that if the singularity is resolved, this assumption is just wrong. And this really, for example, all the things about quantum monogamy are really deeply rooted in this assumption, because the idea up here is that you've got some particle going out, its partner is falling in. If you want to restore purity, then something else should come out before this UH. If there is no singularity, then things can come out after this. The partner mode could just come out and in the larger space-time, and therefore there is no issue about monogamy. Purity does not have to be restored right up to here. So again, the last quickly again, singularity resolution. And as I just mentioned, that Hawking's take 2 in the papers with Pope and Strominger, there is no singularity, but this diagram is still used by others very much. And in loop quantum gravity, this expectation is met in a variety of models that I was just mentioning before. So the kind of diagram that one expects in loop quantum gravity is a diagram like that. You have got sky minus. And then again, in this diagram is a problem that star is not part of the system. So in loop quantum gravity, we'd like to consider the collapse occurring because of some collapse of, say, a scalar field, and gravity plus scalar field is a total system. So we got a closed system up here. And so here is a thick shell, some Gaussian, if you like, which falls and then forms classically to just form a black hole. But what really happens is that there is a dynamical horizon. Dynamical horizon is just a world tube of 2 spheres, each of which is a marginally trapped surface. And so the dynamical horizon starts forming here at the left end of this profile of the collapsing matter, and then it grows. So this dynamical horizon is this black line, and it actually grows. It's difficult to see here just because I think I should have drawn this thicker, and then the statement is it should have grown. Sorry, I should have drawn this thicker, and then it would have grown very much more clearly. It grows, and is space-like in this thing. And then it becomes time-like during the time when the black hole is actually evaporating up here. And if the singularity is actually resolved, then you would have a trap region up here and an anti-trap region up here. And then the statement is that the modes could just come out. I mean, the statement is that the partner modes which fell in could just come out up here. then a lot of open work that is going on is about the completely quantum region, and we can talk about it. Okay, so the expectation is really that, first of all, the important thing is to consider the dynamical horizons, and then the expectation is that that the classical singularity will be resolved and will be replaced by genuinely quantum region, and correlations between the modes which went out at infinity during the Hawking radiation can be restored, because the partners could go through and really obtain up here. And so they don't have to be restored before this last ray, before the last ray appear somewhere here in the semi-classical regime. So now let me go to the second part, which has to do with the semi-classical regime. And I want to say, now I want to forget about really the singularity, and this part has nothing to do with the singularity resolution or with how finally the purification complete takes place. But there's an issue already at this stage that was already hinted at, and that I would like to consider. So I really cut the space-time up here in the semi-classical regime. So I'm not worrying about entering the quantum regime at all. So here is a regime in which, for example, the black hole has shrunk, but to a size of, say, 1,000,000 times Planck length or 1,000,000,000 times Planck length. And therefore, we can just assume that we got semi-classical regime. In fact, I would consider explicitly a solar mass black hole to just go to lunar mass. And I think everybody in the audience would probably agree that this really is macroscopic, and semi-classical physics should actually hold up here. And so the idea up here is that there is a time u, which is green up here. I hope you can see it, this time in green up here. And the statement is that it is really start with the solar mass, and by this time, it has really acquired the lunar mass. The process should be well described by the semi-classical gravity. And this process, however, takes something like 10 to the 64 years. And so a large number of modes escape to infinity during this time. And the total state on this, the total state on sigma up here, first of all, was pure. And the total state on the manifold like that is also pure, because the modes which are outside are correlated with the modes which are inside. So in this region, I got a flat region of space-time before the shell collapses. Then I got the curved region up here. I got radiation, which is coming in, and radiation which is falling in, and radiation which is going out. So inside, I had not only the radiation which is falling in the partner modes, but also the radiation which made the black hole. And this is often ignored. The total state which is pure, if you include what fell in, plus what caused the collapse, plus the partner mode which fell in, and the partner mode and the mode which goes up. All the three together will give you a pure state on this. And then the statement is that the total state up here will be pure. So the apparent information paradox, however, is still there, which is that this process takes about 10 to the 64 years. And just back up the envelope, heuristic calculation would say that there are a lot of modes which are actually emitted up here to infinity during this time. And see, even if the total state is pure, there is an apparent still information paradox, namely that the lunar mass black hole has radius of only 0.1 millimeters. So up here it is only 0.1 millimeters, and the mass is about 10 to the minus 7 times the total mass. Now the radiation which went out, these modes are carrying about solar mass minus 10 to the minus 7 times solar mass, if you like. And what is inside is only 10 to the minus 7 solar masses. So the energy budget, so if in fact all these modes up here are going to be correlated to the modes up here, then there is an issue. One might think that there is an energy budget problem, because I got so much more energy here than in here. Or in terms of modes, in terms of modes that we looked at, here I got a black hole, or I got the dynamical horizon radius is only about 1 millimeter, 0.1 millimeter up here. And if in fact I got more wavelength 0.1 millimeter modes, this is heuristic, then and then I allow the maximum wavelength, which is about 0.1 millimeter, because that's what I think is the maximum size here, then the mass would be about 10 to the 22 times lunar mass. So it's the same argument that the energy budget here does not seem to be appropriate to really account for entanglement with the modes which went on. And therefore, the idea up here is that put differently, the horizon area should account for the total entropy of everything that is considered contained inside the horizon. And this is way too small compared to the entropy associated with what went out. And so this suggests that a significant amount of purification should take place before this time, before the lunar mass was attained. And this general belief is enshrined in the Page curve that restoration of correlation should begin at the Page time when the black hole is shrunk only to half the mass and not to the lunar mass up here. This implies that something goes wrong with the usual space-time semi-classical picture, even when the black hole is macroscopic, even when it is shrinking from half of its solar mass to the lunar mass. But I would like to say that, in fact, there is no problem at all. There is a simple resolution. And the simple resolution is that when one evolves the semi-classical equations, when one uses semi-classical equation and one solves them inside the region up here, one finds the region which is enclosed by the dynamical horizon. One finds that what happens is that there is a very slow dynamics up here that is happening because of the infalling radiation, which is very slow between the time that the black hole is 10 to the 64 years is what it takes. When a black hole is solar mass to a black hole that is lunar mass up here. But during this time, these surfaces that I got up here, you can take them to be Kretschmann equal to scalar equal to constant surfaces, or I can just take it to be R equal to constant surfaces. These are all spherically symmetric. And one can actually solve the semi-classical equation and show that these surfaces develop astronomically long necks in 10 to the 64 years and stretching some 10 to the 62 to 10 to the 64 years up here. And therefore, the radius up here is only 0.1 millimeter, but inside, in fact, these are extremely long. And so the slow dynamical evolution in the semi-classical phase, the infalling modes get stretched, roughly like what happens in inflation, except that this is even much more conservative, because in inflation, this happens very quickly. Here, it takes 10 to the 64 years. And therefore, they become infrared, and one can easily accommodate n of them inside the dynamical horizon. Once we replace...
Sorry, Abhay, I have a comment on this. This is true if you take spherically symmetric modes. If you take modes with angular momentum, then they get, because you get an infinite contraction in the transversal direction, then you don't get this infinite redshift.
Okay, so I'll talk about that just at the end. Okay, so let's consider these spherical symmetric modes for a moment. So so the statement is that there are enough modes in order to, for my argument, that there will be no problem. We'll talk about the other one in the discussion.
But the radiation, the Hawking radiation has the modes which are not.
Yes, so in fact,
well.
Right. So that's why I cut myself in the semi-classical region. I'm not telling about what is happening as we approach singularity. Please wait until the last slide. Once we replace so the statement is that one can easily accommodate these modes. Once we replace the event horizon, dynamical horizon, and study the back reaction on space-time geometry inside the dynamical horizon, the tension with information loss and in the semi-classical regime disappears. And there is no reason for the semi-classical arguments not to be valid for lunar mass black holes. I think Alex would agree with these statements. What happens beyond semi-classicality is what is being debated. But in the semi-classical regime, I think one would agree with this, that there is no paradox up here. In fact, that it better be the truth, because we know that the state up here is pure, and therefore the statement is that these modes which went out should be correlated with modes which went in, and there should be no problem. But then, don't we have long-lived remnants? And this was alluded to about Steve Giddings, with a lot of internal states. First of all, I would like to say that this would happen. Long-lived remnants of this kind are there already by the Page time, when the black hole has shrunk to half the solar mass side. I agree that these remnants then would have, look from outside, would have size of about a kilometer, but for a lunar mass, it would be 0.1 millimeter, and I can shrink it even further and make it an angstrom, if you like. So there are kind of small macroscopic objects which are in completely the semi-classical regime, which have which are lots of modes, and these highly entropic objects is really not an issue at all. And the reason for that is that such objects can exist, but to develop their astronomically long necks, they need 10 to the 64 years to grow, and they cannot therefore be instantaneously created in the particle accelerators or car collisions. So most of us don't agree with these arguments about effective field theory, and we can discuss about that. So let me just summarize that many of us in loop quantum gravity, it seems that several of the standard difficulties disappear if one recognizes that in the classical GR, already the event horizons are useful, very useful, idealized notions, but they are not very useful to analyze actual physical processes. For example, the event horizons can form and grow in flat regions of space-time, as is explicitly shown, for example, in the White-Day space-time. So use of these event horizons as absolute boundaries for the entire evaporation process causes unnecessary confusion. And the second thing is that there is no reason to abandon semi-classical gravity well away from the Planck regime, and one has to carefully study the geometry inside the dynamical horizon. And a very interesting avenue is to understand the relation between this semi-classical description and the recent path integral analysis that Ahmed just told us about. Up at a certain level, I don't see a contradiction, because Ahmed is not saying that the entanglement entropy is, there's something incorrect about the entanglement entropy being large. I think Ahmed is saying that one should really be calculating a different kind of entropy in order to understand the page curve, and perhaps also, if you actually were to make measurements near sky, this is something that Don Maroff and Henry Maxfield argue, the new notion of entangled entropy might be more appropriate. And in all LQG's investigation, the singularity is resolved and is replaced by a transition surface that separates the trapped region from an anti-trapped region. And however, none of the investigations in loop quantum gravity is complete, and there is no unanimity on exactly how the correlation will be restored. Now, there is one recent result, and this is not fully, but this is going towards addressing what Alex was talking about, namely that one can actually consistently evolve the test quantum fields even across singularities, including all the modes, the non-spherically symmetric modes, and the T mu nu, the renormalized T mu nu of such modes, continues to be well-defined distributions, just like they are well-defined distributions away from the singularity. And this analysis provides useful technical tools to unravel the nature of the quantum nature of space-time, satisfying quantum Einstein's equation across what was the classical singularity. So let me stop here.
Thank you, Abhay. Please unshare your screen.
Yeah.
So let's move on to our third speaker, Carlo Rovelli. Please share your screen.
There is a message for you.
Coming, arriving.
Perfect, go ahead.
Okay, wonderful. Thank you, Jorge. Thank you, Ahmed. Thank you, Abhay. We're a bit late, so I'll try to be shorter. I think I can stay less than 15 minutes. I want to make 3 points about the topic we've been discussing, which are these 3. The first one refers directly to the difference between what Ahmed said and what Abhay said. There are 2 different pictures here, and to me, it seems that the picture that Abhay presented is physically reasonable. But if so, Ahmed presented a very strict series of deduction that forces us away that. So I want to point out where I see the confusion comes in a very specific point. And therefore, and this is, I think, is before the central dogma. It's not what come after. It's a central dogma itself that it's wrong. Then I will sort of go a little bit more in the picture of what happened to black hole and argue the second point, that the problem of what happened to black holes, it's actually 3 different physical problems, and we better separate the 3. I'll show what I mean. And then very briefly, the third point, I will illustrate what I think it's the scenario that seems more likely to me, which is in the general framework that Abhay mentioned. And of course, as Abhay said, nothing is certain and sure and complete in this story. So let me start by the first point. Central dogma is a false dogma. Sorry for the Italian O here. It should be an E, a false dogma. And I think, and the false dogma is that the number of internal states, the full number of states of black hole, of a real black hole, I say in a moment why I insist on real, it's bounded by the horizon area. And echoing a little bit what Abhay is going to say, I'm just going to sharpen what Abhay said. This comes from a number of confusion. The key one is exactly the confusion between event horizon and dynamical horizon or trapping horizon, whatever you want to call the quasi-local definition of the horizon that doesn't require to go to the far future, which is related to the last of my points here, stationary evolving black holes. If you assume to start with that the black hole is forever, like the diamonds, and therefore that is sort of something like a Schwarzschild black hole forever, there's an event horizon, then you do the calculation for its entropy, which is the one that Ahmed did, which of course is correct. And you get the thermal entropy of a black hole, which of course is correct. And but that's a black hole, that's a thermal entropy that governs what? The entropy is about heat and work exchanges or something. So this is the heat and work exchanges with a black hole for somebody outside interacting with a black hole as long as it stays in this approximation. As long it is described by an effective event horizon. So before it's evaporate. When it evaporates, it's not stationary anymore. We go out from this approximation, which go out from this regime, something else happens. And then, as I want to argue in detail in a moment, it is the false dogma itself that leads to the page curve and to all the, as Abhay said, the various many tentatives of sort of going around and justify the page curve, which I believe are not justified. The main confusion is between thermodynamical entropy and von Neumann entropy. So allow me, just many of you, this is completely obvious, just allow me just to remind what the two are. Von Neumann entropy is when you have two systems, A and B, a pure state of the two systems, psi A and B, you trace over B, you get, of course, the density metric of the A system. You consider standard entropy, and this is different from zero because there's information in B that you're not looking at. Thermodynamical entropy, in the simplest Boltzmann picture, it counts the dimension of the phase space, which in quantum mechanics counts the logarithm of the dimension. So far, so good. And then Ahmed computed the thermodynamical entropy of a Schwarzschild black hole, and he got a number which we all agree with. And then he said, careful, and of course, the von Neumann entropy is bounded by the thermodynamical entropy because, of course, you cannot have a larger dimension. You cannot have more entropy from here than how big is the Hilbert space of B. Seems obvious, right? And that's, I just copied it from Ahmed slices here. This bounds is fine-grained von Neumann entropy, and therefore is a theorem that the von Neumann entropy is less than the thermal entropy, right? The problem with physics theorems is that they have hypotheses, right? So are we in the hypothesis of these theorems? And one hypothesis that the degrees of freedom are all accessible. So let me give you a counterexample to this theorem, which shows that this theorem is false when you go outside its hypothesis. This is a very simple counterexample. I had one in my old paper, but this is not mine, come from Francesco, I forgot his name, apologies, Francesco. Here you have three systems, A, B, and C. C is the guy here, C for Carlo. And you compute the von Neumann entropy, okay, when you trace over AB. In other words, Carlo gets entangled with AB. So there is some information, some entanglement between the couple AB system and Carlo, okay, which is computed by a von Neumann entropy, okay? Then you take this system, AB, and you just separate the B part and an A part until they are very far away. It's a space-like separation. And now Carlo interact just with A, okay? Interacting with A, there will be a thermodynamical entropy because there are some macroscopic things. And so there's an entropy associated to this interaction, okay, which counts the number of degrees of freedom of what? Of A, obviously, not of B, because it's just because if I put energy into A, it doesn't go into B because they're spatially separated. It's too far, isolated from one another. So the thermodynamical entropy that Carlo sees is just determined by the number of degrees of freedom of A. But nothing forbids that there is an entanglement between, so there is a lack of the impurity in what Carlo measure due to an entanglement between Carlo and B, which is far away. So that's a clear-cut, no relativistic, without any doubt case in which the von Neumann entropy is larger than the thermodynamical entropy. And remember what was in his slide. There is a theorem that this is impossible. Okay? So this is, no, I go to the end and then we discuss. So it's, of course, the theorem is a theorem. Of course, all calculation was correct, but the theorem has an hypothesis. The hypothesis that all degrees of freedom are accessible, all right? So why is this relevant to a black hole? Because that's exactly the situation in which we are in a black hole. The B system, it's whatever happens, let's say on the horizon or around the horizon, or in the membrane paradigm, or whatever you want to think about that. As long as you are in this part of space-time, in this part of Sky plus, if you want, I should take this away. As long as you're in this part of space-time, the degrees of freedom with which you're interacting, sort of that react you back to whatever you throw inside, are only these. So the thermodynamical entropy is corrected, computed by the calculation that Ahmed presented, right? This essentially, as long as you're here, this is a nearly stationary Schwarzschild black hole in which you can do that calculation, and correctly there is this thermodynamical entropy. But this has nothing to do with the fact that there can be a von Neumann entropy that counts the entanglement between whatever is outside and whatever is inside. And this is exactly what Abhay was talking about, right? When there is Hawking radiation that flows out to Sky plus, there's also, if you want, the other Hawking quanta that flows inside and pile up inside, and that's a von Neumann entropy that keep growing, even if the thermodynamical entropy goes back. Of course, as soon as there is a quantum gravity transition and you go somewhere else, I mean, because at the end there should be some quantum gravity things, you go somewhere else, then in the past of the quantum gravity region, so when the observer is here, then we're not in that approximation anymore. So it's you get back the information that you have there. And where is the key here? The key here is exactly what Abhay said, namely, because you can get information through the quantum transition, the interior of the black hole is not screamed from Sky plus, so this is not an event horizon. This is a dynamical horizon or a trapping horizon. So it's something which it's likely the Schwarzschild metric locally, okay, or semi-locally around the black hole. Locally, everything is Minkowski, but around the black hole. But the future is different. But why is everybody getting confused on that? Well, let me remind you, an event horizon is just the past of future infinity. A trapping horizon, for instance, that's one of the definitions, is a region where the area of outgoing null surfaces decreases, right? So physical black hole, that's why I said a real black hole. If you define a black hole as an event horizon, then you're lost because you're killing quantum gravity. Because quantum gravity may very well says that there's no event horizon. And here is the detail. So this is a standard classical picture of a collapsing star, right? The blue region is where you enter in a quantum gravity situation where you can take it when the curvature becomes Planckian, for instance. Then you go outside the classical approximation reliably. But careful. If there's Hawking radiation, the horizon shrinks, right? The local horizon, the dynamical horizon shrinks. And so at some point it becomes Planckian, and the curvature, it's of the order of the horizon to the -2. So when the curvature, when the horizon becomes small, the curvature outside the horizon is Planckian. So quantum gravity just believing quantum field theory field space-time with trivial background, well, how do you say, effect on the metric, the shrinking of the horizon, implies that we're in a quantum gravity regime outside the horizon, which means that the classical prediction that the horizon is an event horizon is not reliable. It's an assumption about quantum gravity, which might be wrong. So that's why to believe that when the black hole presumably ends its evaporation, suddenly all what is inside will disappear into nothing, and we find just because it's a small mass, it might necessarily be that we're near Minkowski and everything disappears. It's an hypothesis which is not granted by anything, is a nonsense. Or in other words, to assume that whatever happens here is screened from Sky Plus, it's a wrong hypothesis. It doesn't follow from absolutely anything. So there's nothing wrong in Ahmed's calculations, except in the point where he said necessarily the number of states for Neumann entropy is bounded by the thermodynamical entropy.
I'm sorry, I need to ask a clarification question about that point.
Sure.
Do you disagree with just a quantum mechanical statement that the von Neumann entropy is lower bounded by the log of the dimension of the Hilbert space?
It depends which Hilbert space, of the accessible degrees of freedom, not of all degrees of freedom.
I'm not sure what that means. So I just have a Hilbert space with some dimension d, and I have a quantum state, some density matrix. I'm just asking about what is the upper bound on the von Neumann entropy of that density matrix of some system. This is just abstract.
Yes, it's sure. No, we agree. It's the number of degrees of freedom, of course, but the thermodynamic entropy can be smaller than that. That's the point.
Sorry, the thermodynamic entropy in a system without a Hamiltonian, or rather when the Hamiltonian is trivial, is just the log of the dimension of the Hilbert space.
No, that's the point. It's the log of the dimension of the subspace of the Hilbert space that include the accessible states. Look, it's not the number of degrees of freedom, it's not the dimension of the Hilbert space of A and B together. It's only the number of degrees of freedom of A. You see, because B is not, I don't interact with it. That's the point. That's a subtlety.
Okay, well, one quick question, because I'll let you keep going. But on this slide, S von Neumann is S von Neumann of what? And ST is ST of what? Maybe let me ask that.
S von Neumann is the trace over AB of the state of ABC, okay, of which I consider the trace of rho log rho.
So it's S von Neumann of C, is that right?
Yeah. After I've tracing away A and B. So it's the entanglement, is the amount of the entanglement between C and the coupled system.
And what is ST? S thermal of what?
Now I'm here, okay, C is here. It's exchanging heat and work with A, only A, okay? And so it's just the number of degrees of freedom of it is the logarithm of the number of degrees of freedom of the Hilbert space of A.
Okay, so this has nothing to do with the thing that I said that. Okay, we can discuss this later.
There's technically nothing that you said is wrong, but at some point you said, and this suggests that, right? I'm not saying that you said anything wrong. I was listening very careful to you. I said, and this suggests that. So we assume that at the end of your, and at some point you flash this theorem, okay? And in this theorem, the von Neumann, the entropy that you're referring to, it's a Becken-Sorokin entropy, right? It's A over 4. Fine. But the von Neumann entropy you wanted to use in this argument is the full number of states of the black hole. And that doesn't follow. Because the black hole, it's the union, if you want, of the boundary, which is like A here, which is what determined the thermodynamic entropy, and the inside, which is what carries the degrees of freedom that contributes to the von Neumann entropy, but not to the dynamical entropy. Notice that I am only, I'm saying exactly the same thing that Abhay said, except that instead of doing it in the detail of a gravitational situation, I'm just abstracting where the point is of disagreement. In other words, there are degrees of freedom inside the black hole that contribute to the von Neumann entropy, but of course not to the thermodynamical entropy. Maybe I should go ahead and
Yeah, please go ahead. Thank you.
Because there are the 2 points. I will fast on the other 2 points.
But just can I maybe just, sorry, Carlo, just a quick remark on that. What you're saying is very true for a non-relativistic system, but then I'm going to say exactly the same thing I said to Ahmed. It is not true in a gravitational system. That is, in a gravitational system.
Well, it's a discussion.
No, but okay, but it's also, yeah, it's a discussion, but it's important to have the assumptions clear. So this point, again, there's an Hamiltonian constraint that link A and B. And in fact, this Hamiltonian constraint is the reason why Ahmed is talking about holography. So at some point, I would put both of you in, if you take into account the fact that the Hilbert space is not split, a lot of your problems or paradox seems to dissolve. And maybe then you can, agree on more.
I don't see any paradox. I'm saying that the von Neumann entropy that measure the entanglement of a far distant observer. So there's no issue about.
Yeah, but you're forgetting that this far distant observer is entangled through the Hamiltonian constraints to A is entangled to B. That's just,
whether it's entangled or not, irrespective of that, I'm saying the von Neumann entropy can be larger than can be much larger than thermodynamical entropy, not just a little bit, can be enormously larger. In fact, the point is that it's perfectly. The point is that the page curve has to go down. There's no region for the page curve to go down. We can have a very small horizon right here. A very small, that's the same thing about we say, a very small horizon. Of course, the thermodynamic entropy go down a lot because the small horizon doesn't has a lot of temperature, but little entropy, as we know. And nevertheless, an enormous amount of information stored inside. That's what I'm saying. There's no reason
to clarify
to
that when you say page curve, you mean page curve for the entanglement entropy, which is what it was. Whereas Ahmed is not talking just about entanglement entropy. Just want to.
I think I am, but we can talk about that later.
Okay.
Okay.
But
So
can I make a comment, please? So imagine, in the sense of what Carlo is saying, imagine a black hole that is macroscopic. So that you trust quantum field theory and curve space-time on it, and you feed it with stuff, with some material continuously, so that you compensate the evaporation. Then you can have an entanglement entropy that includes the radiation entropy of the Hawking radiation that is unbounded. It can be as large as you want, while the area of the black hole is always the same. And in this situation, nobody doubts about quantum field theory, and we know that there will be unitary evolution from one slice to another one. And so in that regime, even though I agree with Laurent, in that regime, what you're saying, Laurent, is also going to be as small as, it's going to be a very small correction that is not really relevant. So entanglement entropy can be very, very, very large, and that doesn't lead to any contradiction. We are in the situation where everything is absolutely clear in this example.
I agree. I agree.
Can I make a comment?
Carlo, please continue.
Yeah, we have a discussion time after. So let me just make the two. This was the first point, point one. Let me get a point two, a point three. I'll be fast about this. So I want to emphasize that I believe that if we want to understand what happened to black holes, we have to solve three physical problems, not one. And unless we solve all three, then we haven't understood it, which I call ABC. And my collaborators here always tease me because I confuse which one is A, B, and C because I put them in the wrong order. So C is that matter, suppose we have a star, the star get inside, become very compressed, is what happened at C. B is what happened at the horizon when the horizon become Planckian or when some quantum effect affect the horizon. A, it's what happened to an observer. This is an observer that falls in. It's away from the stars, away from the horizon. At some point goes there. The universe is not at infinity. Physics should tell us what happened to this observer, whatever it is. I mean, it's going to die, but we're all going to die. So it doesn't change anything. So is it disappearing? What happened there? So there are three different physical problems here. And the A problem, Abhay has mentioned, there is a huge amount of work in loop quantum gravity, and not only loop quantum gravity, which with a number of variants and with a number of things which are not completely clear, but they all suggest that the A problem can be looked at just in the case of the evolution of Kruskal beyond the R=0 singularity. All of them, dozens and dozens of papers with different techniques suggest that you go from this trapedy region to this anti-trapedy region of sort of another Schwarzschild solution here. I like this to call a white hole. Abhay doesn't like the white hole for some reasons. It's an anti-trapedy region that you get when you use quantum mechanics and when you use quantum gravity, loop quantum gravity, different techniques, and go across that. In fact, this is an old idea, goes back to the 50s. One can write a metric, an effective metric that goes through. One can guess an effective metric. The long tube Abhay was talking about, which is the sort of the R=constant or K=constant surfaces that approach the singularity, get squeezed to a minimum and then grow the other side, sort of like a bounce or something like that. The C physics is the physics of a star that gets more and more compressed. At some point, the density becomes Planckian. This is where you expect loop quantum gravity to bound the density or bound the curvature. And this is when you expect a bounce. And a bounce is possible because, of course, a bounce wouldn't be possible in the trapedy region because of causality, but it's possible if you go into an anti-trapedy region. So you can bounce up in the anti-trapedy region. And then the third problem, which is a separate problem, is what happened in the B region here. Because you see, if you continue from a trapedy to an anti-trapedy region, and if the star in some way bounces, what happened here? Are we going in a different universe? And I think here there is a key classical physics result, which goes back a few years, been recently extended to Reinson-Nordström, which is you can actually have a classical solution outside the black hole that continues from the sort of the previous to the future space-time region. So in other words, there is a space-time like that solves the classical Einstein equations everywhere except in a thin quantum gravity, a quantum region. And we know that quantum mechanics allows tunneling. So there is nothing that tells us that this is impossible. Provided that the curvature is sufficiently high. We are sufficient in a quantum gravity regime. It's a standard quantum mechanical tunneling. So this is a reasonable picture of what happened. There is a time during which the black hole lasts. If we believe Hawking theory is the order of m cubed in terms of the original mass, there is what I would call a white hole that forms, which is the anti-trapedy region, which should be connected to the non-trapedy region. So there should be a anti-trapping horizon here. And there are arguments, which I don't have the time to go into, that the duration of this phase here is much longer. Conservation of information, essentially, is M4. So I close with what I see the scenario, which is basically a repetition of the same slide. This is a scenario which it's obviously compatible with quantum mechanics. It's compatible with the Einstein equations everywhere in which in a tiny region. So the only thing we need for quantum gravity to validate that is that the Einstein equations are violated when things becomes of order h bar. So when the curvature becomes Planckian for a little tunneling time. This has been studied by a number of this has been studying, now has been studied using the spin-foam formalism. So the transition, this transition actually has been studied in loop quantum gravity in the covariant picture. I don't want to go into that. I want just to mention this and mention also that there is a lot of phenomenology being studied. That the scenario here is that this remnant are very long living, which, by the way, is the reason you cannot produce them at CERN, right? I mean, there is this old argument by Giddings that you cannot have a small mass object with a lot of internal degrees of freedom. Of course, you can. Okay, they just have to be long living. That's the point. And these are long living. Okay, so the phenomenology which is being explored is relate that to dark matter. After all, the more little things around, there's a possibility of a signal that come out from that. There's a lot of literature on that. I just want to say that it exists. So I summarize. We've been going long. First, I believe that the central dogma is a false dogma because it does not follow from the correct calculation that Ahmed has presented, because there is no reason the von Neumann entropy, which includes the entanglement with the interior, to be bounded by the thermodynamical entropy, which only counts the number of degrees of freedom that can affect us, and therefore near the horizon. Second point, there are three regions, three different physical problems: the tunneling through the singularity, the bounce of the star, and what happened at the black hole horizon become white hole horizon. And the likely scenario is this one, which a lot of uncertain aspect on it. We don't know exactly the duration of the black hole phase. It could be shorter. There have been suggestions shorter. Perhaps some, as you know, Alex Hando Perez has long been said, perhaps some of the information is lost in microscopic degrees of freedom. That's a possibility. There are a number of things which are not clear. This has to be extended to care and so on and so forth. But this is a scenario which doesn't contradict quantum fields in curved space-time where is reliable, doesn't contradict unitarity, doesn't contradict relativity. It's perfectly consistent with quantum mechanics, general relativity. I'm not sure it's real, but I don't see any much more plausible than this. And I'll stop here.
Thank you, Carlo. For those of you who are not regulars here, the seminar has been running for many, many years, and so we have some traditions that predate Zoom. So we thank our speakers the traditional way. So let's thank our speakers. And I thought we could start with some questions among the speakers. And then Ahmed is our guest. Do you have any questions for Carlo or Lee?
Many, I guess.
Let's try one or two.
Okay. So the first is, let me just, hold on. I lost my Zoom. One sec. Can you guys hear me?
We can hear you. Do you want to share something? Carlo should unshare.
Yeah,
then.
do you want me to close it, my slides, Ahmed? Or?
No. It's fine for now. So first, a comment on something that I think it was Alejandro said about, so you can have the situation where you have a black hole which you're constantly feeding. Okay, you're constantly feeding with pure matter, and it continues to evaporate, and but it never evaporates away. You get a steady state solution. But the von Neumann entropy of the black hole, at least as viewed from the outside, looks like it's growing arbitrarily large, right? Because it keeps building up entanglement with all the Hawking radiation that it emits. And you might have said that that's life. That's you should just take this as it is, that the entropy just keeps growing. So two comments. One comment is that it violates the central dogma, which is also an assumption. It violates that from the outside, it looks like the entropy of the black hole is exceeding its thermal entropy. The other comment is that that's actually, that answer is just simply the wrong answer, in the sense that if you do the calculation in the way that I was describing it using the gravity path integral, there's a new contribution that comes in, and the entropy of the radiation, you find that it gets capped out at the thermal entropy, even in that case. In some sense, so this is it's something that comes out of the path integral. This is not something that I've pulled out of a hat. So I'm curious about that possibility for that scenario. I'm interested in hearing.
But I could just take the
But-
Hilbert space.
But in
I could
quantum
just take the Hilbert space as cry. And Alejandro, maybe you should go on.
no, please, Abhay, sorry.
Yeah, so I could just take the Hilbert space as cry and calculate the entropy, and that entropy is, in other words, you're calculating some entropy, but that is not the entropy that I would calculate. I mean, the best way is to avoid this issue about the Hilbert space and just focus on observables. So I can just consider the algebra of observables associated with cry, right? And calculate the entropy, and that entropy will keep growing.
I disagree. I mean, you can compute literally trace rho log rho, and you compute it in this careful way using the gravity path integral.
But
And
I can just calculate at scry, right? I mean,
yeah. Calculate it.
you give me this. I mean, I don't need to know anything about entanglement. I can just calculate the. I just need to calculate knowing what the state is at scry.
I think I agree with you in what we want to calculate. So what you want to calculate is trace rho log rho of the region far away from the black hole, right? This is what we want to compute.
Yes.
And what I'm saying is that when you compute that quantity, there are contributions that come in, which and like if you compute trace rho log rho as trace rho to the n and then take n goes to 1, you get contributions which are wormholes connecting the different copies, but they get connected inside the black hole. Like this,
but that's a certain Euclidean calculation that gives you some answers. I agree with that. But I could just calculate it in the using algebraic quantum field theory at scry. And I would not get that. I would actually get just, the thermal, the entropy corresponding to thermal state at scry. And the Hilbert space at scry, I got a Hilbert space. I got a thermal density matrix there. That's what I would get.
But don't you find it odd that that calculation, it has in it a contribution, which is exactly what you're saying, but it also has another contribution.
Yeah, therefore you're calculating something else. I mean, in other words, in normal systems, which are not gravitational, various calculations give you the same answer. But once you include gravity and particularly, non-trivial things like black holes, then the same calculation that you're used to in flat space-time and, quantum field theory in flat space-time, etc., could give you different answers. I think that happens very often.
But I find this really weird because I thought coming into this community that you guys would give more weight to gravity. But here you're telling me I'm going to ignore the new thing that gravity tells me.
But can I make a comment which goes along the same lines, I suppose? If the black hole is very large, if you take a slice and you're feeding it in the way I proposed, and you take a slice, some spatial, some Cauchy surface for the past part of the, and then you take another one to the future, then because the black hole is large, then to a very, very good degree of accuracy, there will be a unitary evolution of the quantum fields from sigma 1 to sigma 2. And there is absolutely no paradox. And then I can compute the entanglement entropy. It's true, there will be a divergent term proportional to the area. I can put a cutoff. But, I could regularize this in some way. And that entropy will be growing due to the fact that I am producing more and more Hawking radiation. And there is absolutely no paradox in this. So don't you agree? Because I know that in quantum field theory, the evolution from one sigma to the other is just perfectly unitary. Why should there be a paradox when there is nothing? And everything is absolutely clear in this situation, in the regime where quantum field theory is an extremely good approximation.
I agree that there's no obvious reason for why you should distrust the quantum field theory.
No, I'm saying there is no paradox. There is no problem. There is no need to go to your calculation. I mean, in my view, this is my confusion.
No, but what I'm saying is that one should do the calculation carefully, irrespective of what answer you want to get. Okay, yeah. And all I'm saying is that there are contributions that come from wormholes that change the answer, that are different from the naive expectation that quantum field theory on a fixed background gives you the right answer. This is an observation. The question is whether you want to trust the calculation or not.
No, I think this is really the interpretation of the calculation, not the calculation itself, right? I mean, again, as I was saying that, I mean, I agree that this community will trust gravitational things much more, but we trust so much that we also believe that when you include gravitation, then the same physical concept in absence of gravitation can split into distinct physical concepts. And just to have this, since we had this slide up here on the screen, I mean, why could you not be calculating just the entanglement entropy, or entanglement entropy between just A and C, and in the Euclidean calculation, and not with the combined system A, B, and C. In other words, these extra terms that you're getting in the Euclidean calculation, you're getting some answer, but it's not clear to me that that answer is the same as the entanglement and entropy between the original system AB and with C.
Well, in terms of the picture here, I mean, I can maybe draw some pictures for you, but I'm saying in terms of the pictures here, I would say that the calculation is set up from the beginning to compute only the entropy of C, okay? And then what you find is that it also includes B in the game in some way. Like that comes in from gravity. I can draw some pictures if you'd like, but
the entropy of C, namely C has a density matrix. Is that what you're saying?
For me, yes, C is some region far away from the black hole, and I'm computing.
Right. That's here we are together, and there's a density matrix associated with it.
Correct. Is it okay if I draw, if I share my screen and draw a picture?
Sure. Let me take this away. Just 1 second. You cannot do it while I'm doing it. Blah, 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 blah. Here.
So while we wait, so you're doing the clear calculation, but there's something happening inside of the black hole. Could you give more details eventually about this? I mean, inside, I don't know what the weak rotation mean. I don't know what this Euclidean saddle are. You didn't give many details.
Yeah, because 15 minutes is not enough time.
You know, I understand.
Let me first join.
But do you get it? Do you get what is the point of my question? So normally when you go to the Euclidean, you only get the exterior. Where the analytic continuation gives you a real metric.
If you go to the interior, then you continue to Lorentzian time, then you get the interior again.
I think Alejandro has a point here. It's the way you derive your first calculation, the easy one, the one you use to derive the thermodynamic entropy. Your Euclidean space has a boundary. And the boundary, it's an S2 cross an S1, if you remember right, which is essentially the horizon going from past to future and then close, because you do the thermodynamical thing, you close the past to the future, right? Essentially, that's it. You know, it's clean version of the old, what is it? Hawking, Hartle?
Gibbons.
First Gibbons. Oh, Gibbons, thank you.
It's Gibbons Hawking, yes.
Gibbons Hawking, thank you. It's a clean version of that. Which of course it's nice, it's correct. It gives a thermodynamic entropy, but point is, and how is saying is that which thermodynamic entropy is given? It is given a thermodynamical entropy of a black hole, which is assumed to be stationary. Okay, it's key point of the thing, where you cut away the interior, you forget the interior, okay? And so you're asking, if you're outside, okay, and there is some thermodynamical effect of the horizon, what are the thermodynamical effect of the horizon? And that's fine. The thermodynamic effect of horizon give a quantity which you correctly call an entropy, and we all agree, it's all fine. The point of disagreement is that this has nothing to do with the fact that this calculation doesn't see some physics. And the physics is a physics which is not captured by the analytical continuation of the exterior of the horizon, because it's the physics of the entanglement between the outside and not the boundary, but something which goes inside and which only becomes effective for an observer when the horizon is not an horizon anymore. So when we come out from the. Let me make a comment since I have the floor, and then I'll shut up. Theoretical physicists are super good, notoriously, and you're one of the best. So once you give them a problem, they find a solution of it. Okay, if you take the central dogma and you want to justify it, I'm sure that somebody sufficiently good find a calculation that. But the point is, as you said, that the central dogma is an assumption. You said it so in your, and it's an assumption which physically is not justified. So what's the point of making an assumption, getting in trouble because it seems to be, and then climbing mirrors to find a very smart argument that makes it compatible with the rest? Just assumption is wrong.
I disagree. Well, so I don't want to go into sort of overviewing the entire field of string theory and ADS-CFT and blah, 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 all of that stuff. But I would say there's a lot of evidence pointing to that central dogma. And we're trying to come up with, all of us are trying to come up with the best description fitting all of our data points. We might disagree on which data points should have higher credence versus others. All I'm saying here for this talk was just about how the gravity path integral gives us answers consistent with this central dogma. That's really everything that I'm saying.
Right. So we had a talk with Maxfeld, a year ago, and I had a long correspondence with him and with Don Marolf as well. And Don completely agreed at that time, at least, that in fact what is being calculated with islands is not the entanglement entropy, and that the entanglement entropy would continue to grow, and he didn't see any problem with that at all. He said that what one is calculating is an entropy which is kind of more relevant in terms of actual observations near Scry, and that I understood to mean certain algebra of observables or something that you construct. So even within string theory, Dong has the same ammunition as you in terms of string theory.
Can I draw a picture?
Yeah, please.
So let me show
or explain to me that you disagree with Don and why.
I'm pretty sure Don agrees with me. So okay. I'm confused about this.
I can share the message on the screen if you like.
Okay, so let me. One sec.
While Ahmed draws, does any of the other speakers have a question?
You mean questions to speakers? Or?
Okay, can you guys see my screen?
Yeah. Yes, go ahead.
Okay, I'm doing something. Okay, I'm going to draw a picture. The physical significance of the picture might be not very clear to everyone, but I'll tell you which features I'm trying to. Well, hopefully, it's going to get the message across. So, let's do something like this. So, here is the usual cigar geometry. Okay. Let's imagine breaking it up. Well, not breaking it up, but
wait. What is the boundary? What is the boundary?
Well, it's S. Well, the
no, physically, what does that represent?
Oh, it's not a boundary. It goes all the way to infinity.
There's a boundary there. The S1, or it's not an S1. The boundary.
The horizon. I think Carlo wants to know what the horizon.
No. The manifold here asymptotes to S1 tensor RD, let's say. Okay, so this is the S1 direction, and the RD, and every point here is a D-1 sphere, and there's a radial direction, and this is RS, the Schwarzschild radius. Are we good so far?
The Schwarzschild radius, I'm confused. What is the Schwarzschild?
These are Euclidean.
But the Schwarzschild coordinate, you mean?
This is a Euclidean black hole.
Euclidean black hole, that's the point. And therefore...
Are we good so far? This is the Euclidean black hole.
No, I don't understand what is the boundary physically. What does it represent? Is that the horizon or is Scry?
No,
is something else? There's nothing of that. There's no Scry. It's some infinity boundary. Where is it in space time?
This is at infinity. This is at infinity. I don't have a boundary. I'm drawing the cigar geometry in asymptotically flat space.
So is there an area somewhere here in the boundary or not?
The area is here.
Where?
The horizon is here, this point here.
In the Euclidean space, the horizon.
This is an analytic continuation of the outside of the horizon. Is that correct?
Correct.
So this already cuts away whatever happens inside the horizon. Is not an analytical continuation of the inside of the horizon.
Correct.
Good.
Okay.
So the boundary I should have focused is not the right one, is the left one. And that's, and there is an area there. Okay, good.
Yes. Okay.
There's the
Okay, got
point
it, got it,
there,
got
which
it.
is really
Okay,
an
well,
issue.
Yeah, it's
Very
like
good.
the origin.
Very good. Very good. Now,
Yeah.
let's imagine flattening this cigar. So I'm going to draw this cigar like as a disc. Okay. This point here is RS.
Mhm.
Okay? And this guy is at infinity. Okay. Let's do that.
Got it.
Okay. If you consider a slice like a, if you consider a slice like this, that's like this slice here. Okay. That's like a slice of the outside of the black hole. Do we agree?
Yeah.
Okay. Let's imagine for the moment that we want to compute the entropy of some region outside the black hole, this red region here. Okay. So that in this picture, that's like a red region here. Very good. How do we compute entropy? Okay. So one way to do it is to say, let me just consider the state of the matter. Okay, I fix a geometry and consider the state of the matter and then compute, trace rho to the n and then take n goes to 1, blah, blah, blah. Let's do something much simpler. Let's just consider n equals 2. Okay, this is the thing called the purity. The way you do that is you consider 2 copies of the system because it's trace rho squared. There's matrix multiplication of the 2 rows, which means that you draw a cut along the region you want to compute the entropy of, and you identify. You do some identification like that.
Okay.
This is trace rho squared. Okay. This is how you compute the density, the purity of the matter. Okay. Of this region, assuming you've quote unquote turned gravity off. Okay, so you're just doing path integral of matter on a fixed gravitational background. Okay, so this is what I would call computing trace expectation value of rho all squared. Okay. Expectation value, I mean plugging in a gravity saddle. But now what I'm saying is that this is too quick. This is not the thing that you should compute. The thing you should compute is trace rho squared and then evaluate everything by saddle points. But what does this quantity look like? So this thing is, again, let me draw it in a different page, or actually let me draw it here. You can, again, the setup of the problem is that you consider the same thing with the right identifications, and you consider all possible saddle points. One saddle point is what we had here, which is, so here gravity was filled in like this. So gravity is filled in like this. But there's another saddle point, it turns out, where you develop a wormhole that connects the 2 disks. Okay? This is something that you find in the gravity path integral, but it's a thing that you find if you evaluate it this way. Okay.
But in the Lorentzian gravity path integral, there are things there that you don't see in this Euclidean version, right? There are many metrics that are not real when you complexify time. I mean, there is no weak rotation in gravity. So
yes, I agree. But there's something amazing that comes out of this calculation. So let's consider this. Let's consider this picture. Okay, this picture you can draw it in the following way. Here's my disk. I'm going to use a so-called quotient picture. Okay, which means that here is well, actually, let me draw it slightly differently. I have a branch cut here. This is the branch cut that tells me that that makes the identification between this part and this part. But the fact that I have a wormhole here connecting the two sheets tells me that I should have another set of branch points and a branch cut. Okay. This picture is supposed to represent this picture. Is that clear? I will address your question in a second, Alejandro. First, is this clear?
No, it's. I mean, this is technicalities. What are you?
No,
I mean,
no,
I don't
no.
think this. I
It's-
understand you're enthusiastic about this calculation. Very good.
Please, Carlo,
No, that's not the point.
let me get the following message across. What I'm saying is that when you compute this quantity, there you can get a contribution from gravity that connects a wormhole from the first sheet to the other sheet. That's my first point. Okay? And I hope
from some sort of Euclidean quantum gravity.
For now, let's say yes. Okay, and I'm saying that I can represent this picture as this picture here. Okay, that's what I'm saying. Because this branch cut is just supposed to represent the fact that I have a connection between the two sheets. Maybe I shouldn't belabor this point, but the upshot is when you actually try to find a solution for this, you find that the location of this wormhole is actually not in Euclidean space. When you actually look for a solution, you find that the location of this branch cut and these branch points is actually in Lorentzian space. So when you go and then draw a picture of the black hole, here's my Lorentzian black hole. Here's the region outside that we were computing the entropy of. What you find is that the space-time these branch points here, actually, they look something like this. They move into the Lorentzian section and they give you a picture like this.
How? I mean, by what procedure you see this thing, that this wormhole turns into something inside?
Good. So what we're trying to do is we're evaluating this quantity via saddle point, right? And so you need to look for the solution of Einstein's equations. And the solution of Einstein's equations, it determines the location of these branch points. And the location you find is not in the Euclidean section. You find it that it's in the Lorentzian section. Like it's literally just an output of the calculation.
Solution of Einstein's equations the saddle point of
how can that?
the,
I mean, you're just summing over Euclidean metrics. How can you find a
right?
No, I'm not doing that. I have some path integral e to the I g, and I'm just looking for configurations that extremize the action. And you find that given the boundary conditions of the problem, the configurations that extremize the action are not purely Euclidean configurations. They have a Lorentzian part.
So are you saying that the picture you drew of a wormhole is not quite right because that would be an Euclidean configuration?
Exactly. This is just for intuition.
So this is just a bookkeeping type of language, but what you're doing is something else yet. It's not really that.
I think the right thing to say is that it's the Lorentzian continuation of a Euclidean wormhole.
Okay.
Sorry. No, let me take a step back.
No, because the Euclidean wormhole came from the Lorentzian picture, and we know what that corresponds to.
That's why I wanted to step back. I realized that I misspoke. You can have a wormhole in the Euclidean section. Okay, there's a location of the wormhole. Then what gets continued is the location of the wormhole. It's not the continuation of the Euclidean wormhole spacetime. No, but the location of the wormhole gets continued to Lorentzian space, and that's why you get a picture like this.
Okay, in the wormhole picture, this wormhole is connected to regions where the spheres have a radius which is larger than the radius of the horizon.
But then Okay, fine. That's a good point. In the case where this calculation actually applies, the island ends just outside the horizon, but that's a detail.
Let's see, since we are
It's not detailed, right?
to our mark, could we take a few questions from the audience? Raising your hands with Zoom, please, to keep some order.
Okay, let me unshare.
No, I think just before you unshare, I mean, you don't know how to do the Lorentzian integral that you, or the complex metric integral that you wrote down. It has absolutely no control. The bottom thing that you wrote down, so long as it is a Euclidean domain, or so long as G's are all Euclidean domain, there is some semblance of control of that. And you can do this, some saddle point approximation, etc. As soon as you go to complete Lorentzian domain, I mean, I is, that integral is just not well defined. I mean, it was never well defined, but now it is uncontrollably well defined. So I'm not sure that the arguments apply at all in this case.
Well, as you said, Abhay, like this, nobody knows how to do this integral. The only way we know how to do it is to look for saddle points. And
Yeah, but
please, what I'm observing is that there's a saddle point which is in the Lorentzian section.
Right. But now exactly going back to what Carlo was saying, now the question is of interpreting these saddle points. So it may be that what one is doing is really calculating the entropy that really has to do with the surface degrees of freedom, as in Carlo's language. Because, I mean, one is taking for granted, this is exactly the point I was trying to make, but it was too vague, that when you do the actual calculations, there are new elements that are coming. And those new elements might tell you that the quantity that you calculated is not the usual quantity in, flat space-time or curved space-times without any horizons, but it may be a different quantity. So it may be that you are calculating this quantity, and that quantity, and it seems to make complete sense if you say that quantity is really the degrees of freedom of the black hole horizon that interact with exterior. Yeah, and then everything seems to make complete sense. So the whole question that for us is really the interpretation of the last step you did, which was really completely stepping out of the premise that one started out with in Euclidean path integrals.
I disagree with that.
Before you answer, Ahmed, let me add one point to this.
The question is set up by your initial setting up of the question, like this.
Absolutely.
And the initial setup was this computation, and then we just see what gravity wants to tell us. If you want to reinterpret the result at the end, that's. I mean, if it quacks like a duck, it's a duck to me. So please go ahead.
Ahmed, that's fine. You're doing gravity, right? But now, suppose there's an extra field, or there's an extra volume of the Encyclopedia Britannica which is thrown in. Your calculation doesn't know anything about that. I mean, what I mean is that what we are worrying about is that on a black hole, real black hole, there is also, on the black hole geometry, there is also another field, whatever, that Hawking evaporate and that create additional entanglement between the outside and the inside. And this depends on what else I'm throwing inside. So of course there's more entanglement with the inside if I throw more thing inside. How can your playing with a functional integral of gravity alone know anything about that? It doesn't.
Oh, it does. So this gravity path integral also has a matter path integral in it. And that is sensitive to things like throwing things inside.
How can it be insensitive? I mean, I throw something inside. Immediately after I throw something inside.
It is sensitive. It is sensitive. It is not insensitive.
No. I don't think we're convinced. Let's put it this way. It's a beautiful calculation, but I don't think we're convinced that it's relevant for the difference between the thermodynamic entropy and the von Neumann entropy.
Yeah, I think there are new elements that are coming in exactly when you went to the complexes and when you're trying to do things. And then the physical interpretation. I mean, if I just say that what you're calculating is in fact the number of degrees of freedom on the exterior or the entropy associated exterior, which actually agree with which can interact with the degrees of freedom on the surface of the black hole, then everything is perfectly fine. So, and I don't see how your calculation is telling you that you're not doing that. I mean, you're putting new elements in the calculation, and so the physical interpretation at the end can be different from the traditional physical interpretation with the traditional calculation.
I don't know how to answer that. I mean, it's just, I mean, here it's,
yeah, but I think it's just, I mean,
this is
we do that all the time, right? I mean, in general relativity, that certain calculation that you do in special relativity can give you two, like, for example, like, I mean, even within general relativity, you know, you can calculate the mass of the space-time, for example, by having planets go around them. You can calculate it by what happens to the mass if you actually have a bunch of test particles and you observe their geodesic separation, and you get different answers. And when, I mean, and the statement is that, yeah, I mean, there's nothing wrong. I mean, because, you know, in Newtonian theory, you might get exactly the same answer, but in general relativity, if it is not stationary space-time particularly, you will get different answers. And we say, yeah, that is because the concept has bifurcated, and we have to really carefully trace as to which, that the given calculation, which concept it really refers to. Even though in Newtonian theory, it all coalesced and gave us the same answer. So here you're doing a certain calculation, but it seems to us that the physical interpretation you're giving to it at the end, sticking to the starting point, is not necessarily relevant because, or is not justified, I should say, because you have put in new elements in the calculation.
It's the gravity path integral that's putting them in. It's not me.
No, but I mean, it's the same thing that one is. Yeah, okay. I think that it's not, I mean, it's true that it's a gravity path integral, but you are evaluating it by putting in new elements, which are not there in the gravity. I mean, in the beginning, when we associated the meaning using the Euclidean path integral, that was perfectly fine. What thermodynamic entropy meant. But now you're doing something else. And therefore, when you do that, it may well be that, you know, seems completely justified to us to say that, yeah, it's a very interesting calculation. And look, what this calculation gives us is really the entropy associated with the degrees of freedom which interact with the surface of the black hole. And if I say that, then I mean, we would all, there's no contradiction with anything. And also the page curve going down and so on, everything seems perfectly right. That the number of degrees of freedom which can interact with the black hole is going down as the area shrinks. So to us, it all looks completely sensible, and it's an interesting and fascinating calculation that one can get to the number of degrees of freedom that interact with the surface of the black hole in this particular way. But I don't see why one is compelled to say that that's not what it is. I mean,
we're not here to convince one another, right? We're here to
Right.
exchange point of view. So it's not, the point is not to get to a consensus. The point is just to present different views that come from different ways of viewing a problem, and to sort of listen to one another. So that's it.
The point is to make sure we all understand each other's points.
yeah,
It's,
right. Exactly.
yeah.
Shall we take some other questions?
Yeah. Let's take questions from the audience. Sorry, I just.
Jingjia has had a hand for a long while up.
Thank you. I just have a quick question to Ahmed about saddle points. I wonder if you have any selection principle if in the gravitational path integral there are multiple saddle points. For example, I mean, in the context of a more general case, not necessarily this model you're considering for simple black holes. I can do a gravitational path integral in general, given some boundary conditions. And for some boundary conditions, there are multiple saddle points. Do you sum over all of these in your semi-class calculation, or do you have any way to select the relevant ones?
I think I just do things, well, not just me. I think the right thing to do is to, in this setting, you just, you try to list all this. Well, we can't do the integral, so we can only look at saddle points. And then you just, in theory, you have to consider all of them. And then you pick out the dominant one. So the selection criterion is just what's the best approximation for your integral. And in this case, well, there's a transition between the Hawking versus the wormhole or island answer at the page time.
Seems you're saying you do some or all of these, but some are dominating. So these make major contribution.
Well, in this particular calculation, we only have 2 saddle points. And
But I'm asking in a more general case for the gravitation path integral. In theory, do you sum over all of these, or do you select some?
You sum over everything, and sometimes you also, yes, you sum over all of them, and then and that's it. And then your answer is going to be dominated by whichever one dominates. If that happens, or maybe the sum resums into something. I mean.
Oh, thank you.
Yeah.
Edgar?
Hey, sorry, Ahmed, can you scroll down to the picture with the island and the black hole? I want to see if I understood the perspective of the other speakers. So Ahmed was trying to argue that you set up a computation to compute the von Neumann entropy of the radiation far away from the black hole. And what you land on, what's represented in this picture, is that the answer for that question is roughly given by the semi-classical entropy of this region R, this radiation region union the island region. And I think what the other speakers were saying is that you can interpret this computation as computing the entropy of the degrees of freedom that interact with the surface degrees of freedom of the black hole. So by that, is it meant that really what you're computing is the von Neumann entropy of the radiation union the island region? Is that a way of rephrasing what the other speakers are saying? As opposed to the semi-classical entropy of the radiation union the island?
Yeah, I guess, I mean, I'm not sure exactly, but something along those lines, not exactly. Yeah. Yeah, okay. Yeah.
And just to make sure I also understood, so both Abhay and Carlo, is very important that you sort of disagreed with the central dogma. The number of states of a black hole is more than e to the a over 4g. I mean, that was just motivational in Ahmed's discussion, but nevertheless, one can take votes and see where they land. But it was very important that that was not the number of states of a black hole in your guys' discussions. Is that right?
Yeah, so in my view, I mean, there is a difference. I mean, this was first surprising to me, but there is a difference between the old black hole and the new black hole. When the black hole is just formed, of course, there is nothing outside. I mean, let's suppose that there's a scalar field collapse, and that's the black hole just formed. There's a coherent state which comes from sky minus, forms a black hole. Then the statement is that, yeah, then I think then the area of the black hole, you could take it to be the gravitational entropy. So because it is really just the surface degrees of freedom which interact with outside, and so there's nothing inside. So then it is the total entropy. But as the evaporation proceeds, more and more things will fall in, and then it is no longer the total entropy of what is contained inside the horizon, but rather it is really associated with the degrees of freedom of the horizon which interact with the external world. So it's always the degrees of freedom which interact with the external world. But for a new black hole, so to say, there is it can also be taken to be the total entropy. But as the black hole becomes old, evaporation proceeds, then it's no longer the case.
Thanks.
Yeah, in fact, I think, I mean, Abhay and I got to this in independent ways of thinking, but there's, for me also the big surprise and the big point of all that was the distinction between an old black hole and a young black hole. So two black holes with the same area, classically, are very different geometries, depending if they formed just now by a collapsing something with that area, or long ago with a much bigger area and they have shrunk by Hawking radiation.
So there's very different geometry inside the horizon.
Yeah, in fact, something pretty magic is true in classical general relativity, which is they have very different metrics inside. You just write the metric and it's very different. But from the outside, you do not see the difference at all, okay, unless something happens quantum mechanically that transform the horizon, that kills the horizon in a sense, that has as a consequence that the horizon is not an event horizon. So is this point the crucial one? I mean, unless one realizes that what may happen physically is that the horizon is not an event horizon, one doesn't see, one cannot start discussing what happened at the singularity. And Abhay was insisting the physical problem is what happens at singularity, the singularity resolution. All the calculation of Ahmed, which are very nice, very good. In fact, I want to learn more about them. And it's somehow they're all in the implicit assumption that the horizon is an event horizon. So it's everything seen from the outside without going past the quantum gravity transition, whatever happened at quantum gravity transition. That's what I would like to know. I mean, if those methods could say something about not a stationary object. A stationary object is an horizon doesn't end the evaporation. The physical problem that I think we should all address is what happened at the end of the evaporation, not as long as this thing is evaporating. Because if we keep thinking, oh, we just have to understand what happened at long as this thing is evaporating, we're just always avoiding the physical problem. And it seems to me that we have means. I mean, in loop quantum gravity, certainly we have means to study what happens at the end of the evaporation. So when you got to the little wiggy line in the picture, which is out there, and there it's completely different, where the actual distance between the horizon and the R equals 0 on the left side is short or large. A black hole has a huge spatial distance between the horizon and the inside, and this distance is what it's completely lost in the kind of calculations that treat the black hole as a stationary object with an event horizon. I shut up. I'm very curious to know what is Hal's question, so I'll shut up.
What's that, Hal?
So I actually had a somewhat technical question for you, Ahmed. It's about the nature of these saddles. So I suspect you know this recent work of Kontsevich and Siegel, and also Ed Witten has been thinking about these things. About this follows up on old work of Jorma Luoco and Raphael Sorkin about the viability of certain complex metrics as saddles. And so I was curious about these island saddles, and whether you know whether they satisfy these sort of viability criterion of Luoco and Sorkin, and whether we can think of them as really complex saddles that are related to a Lorentzian metric.
That's a great question. Unfortunately, I don't know what the answer is for these configurations that I talked about, but I do know that some people are thinking about this, and well, so far I remember that some class of them satisfy this, and well, there was one example which is luckily not relevant to an evaporating black hole, but something about something about being entangled with a de Sitter closed universe, which I think has some problems related to what Witten pointed out. But yes, I don't have a straight answer for you. Maybe somebody else has thought about this, but I agree that it's a very interesting thing to investigate, to see if that rules out these configurations or adds more support.
Yeah, Edgar, I'd be curious if you have an opinion. You know, speaking of wormholes, we could think of wormholes in all sorts of unphysical situations, right? Where you would have to have negative energy, and they could be very unphysical. And this would be a criterion for rejecting unphysical versions. I'm not saying that yours are. I'm just saying that it seems interesting to figure out whether we can eliminate them on this basis.
Yeah, I agree.
Yeah, no, it's a great question. I think that all the things that descend to an island saddle in the semi-classical space-time, as Ahmed has drawn here, I think all of those are always going to satisfy the condition, but that hasn't been shown. I mean, there are crazier wormholes you can draw that wouldn't descend to something simple in the original space-time, and those probably will be ruled out, or at least some of those.
Yeah. Thanks.
Well, folks, it's been over 2 hours by now, and our speakers are sort of looking tired by now. So I'd like to thank the speakers again.
Can I just make one comment about this thing? Sorry. Just one thing. I mean, one of the good thing that might come out of this is really, this calculation was done in which the kind of if you like, I mean, as Carlo was saying, that in the Lorentzian domain, there is a dynamical geometry inside the horizon, and that dynamical geometry is pretty dramatic, and that somehow could be captured by some idea like this, where one is really calculating, doing a Euclidean calculation, doing this complex thing, etc. But that is capturing the physics of what is happening. But again, in our view, then that would be correspond to calculating the entropy of the surface degrees of freedom. Yeah. So because here there's no dynamical geometry inside, right? I mean, all these geometries are, is that right, first of all, that all the geometries in Euclidean domain are not really dynamical?
Well, if you continue to Lorentzian, they are dynamical now.
Why? I mean, so what is the geometry that you're written down up here just inside the horizon? I mean, how does it compare? That would be fantastic. So does it compare in any way with the geometry that we find, or anybody finds by just looking at the solving the Einstein's equations with the stress energy tensor given by the flux?
Would you say that the maximally extended Schwarzschild space-time a dynamical black hole or not?
No, not at all.
Um,
No, that dynamic in a trivial sense. I mean, no, but that not, no. I mean, like this surface is developing long astronomical necks is dynamical. I mean, that kind of non-trivial phenomena that just comes out of some, a very conservative calculation in semi-classical gravity, just taking solving the Einstein's equations with, stress energy tensor of the infalling matter.
But sorry, Abhay, I thought that the eternal Schwarzschild black hole, that the length inside does grow arbitrarily large.
No, but this is really time-dependent mass, right? It is.
I understand that aspect. But I was just pointing out that even for the eternal black hole, that the length of the interior does grow arbitrarily large.
But you're not doing here eternal black hole in the picture at least. Right?
I know.
Okay. So I was really referring to the picture up here. But no, but the dynamical in the sense of our dynamical in the sense that solving the semi-classical equations, right, with the stress energy tensor, you get Vaidya kind of metric, and which is not a Schwarzschild metric. It's not. If you like, these metrics are not source free, whereas Kruskal is source free. So they're quite different.
Yeah, I think there are actually. Well,
but then it's not true that the matter doesn't matter.
I think there are examples of this calculation for dynamical black holes. Maybe I can send you a reference.
Okay, thank you. So sorry, Jorge, I just.
Okay, thanks everyone, and perhaps we can repeat this at some point in the future.
So thank you.
And thank you very much, Ahmed, for both participation, patience, and everything. Thank you.
This was a lot of fun. Thanks, guys.
Okay.
Bye-bye.
Bye-bye.